we're looking at the arithmetic progressions, and we could finish a few of the problems over there. Now we'll move on to the next type of progression, that is geometric progression. Okay, in order to define a geometric progression, uh, it is a sequence of numbers with a constant ratio between every number in the series. So that means if I divide a number by its previous number, I'm going to get a constant ratio. Okay, so geometric progression, it is a sequence of numbers whose first term is non-zero and each of the term is obtained, right, multiplying its just preceding term by a constant. Okay, and the constant is called as common ratio of the geometric progression. Okay, now let us try to define this. Let there be n number of terms, and we'll consider that to be GP, and then we'll consider what is the condition for that particular sequence to be a GP. So let's try to assume that let the terms be T1, T2, T3, dot 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 up to Tn be a it can be finite or it can be infinite sequence, doesn't matter, right? Both can be a geometric progression. So we have to make sure that let this be a progression such that there is a condition, specific condition that has to be met by the geometric progression, that none of the term can be zero. If any one of the term is zero, after you get a zero, if you multiply by any term by zero, all terms become equal to zero. That's why, right, none of the Tn can be equal to zero, right? Specifically, the first term can never be equal to zero, that's for sure. If the first number becomes zero, then all the other numbers will be zero, right? So such that okay, I want to write it as any of the Tk is not equal to zero, such that say any Tk is not equal to zero. Okay, and if this condition is met, that you Tk divided by Tk minus 1 is R, right? If this is a constant, then the progression is said to be the geometric progression, right? So this R is called as the constant of geometric progression, which can be found by dividing any of the term in the geometric progression by its previous term in the same sequence. So we'll write like this. So T2 by T1 is equal to T3 by T2 and so on. This is equal to Tn divided by Tn minus 1 is R. This is called as the constant of the geometric progression. Okay, now let's try to find out some of the basic features of this geometric progression. So we'll begin from the first term, and by default, we'll denote any of the first term of the progression by small letter a. So let T1 equal to a be the first term of the geometric progression. If that is the case, then you can see that T2 can be written as A into R, right? There is one R that is coming up in this. So if I try to write the T3, then that should be T2 into the constant. That is T2 is AR into R, so AR square. So I can write T4 as T3 into R. So T3 is AR square, becomes AR cube. In the same fashion, I can try to write the last term, that is Tn, can be written as this is Tn minus 1 into R. So you can see that for 4, this is for 3. For 3, this is 2. For 2, this power is 1, and so on. It's 1 less than the term's n value, right? If n value is 4, I can see that AR to the power 3. So nth term can be directly written. Tn is equal to this is a into r to the n minus 1. So nth term could be like this. So this is what is called as the nth term of the geometric progression. So nth term of geometric progression is like this, right? So actually the geometric progression can have infinite terms as well, right? But we don't try to find the infinite the last term, right? Because it is not possible. We can try to find any n value using this particular equation. All right. Now let us consider some of the facts about the geometric progression in the form of a note. Okay. So the first point is that in GP, A cannot be equal to 0 and even the R is not equal to 0. R cannot be equal to 0. If R is 0, after that all the terms will be 0, right? And if even A is 0, all terms will be, right? This is the first thing. And right, again, in geometric progression, any value of Tn can also not be equal to any nth term is also not 0. The ultimate meaning means you cannot have any of the term being 0 in the geometric progression. This is obvious. All right. Now, let us say that we have a GP and the terms are alternatively positive and negative, right? Then the common ratio is negative, right? So this is the conclusion. So if the R is less than 0, this implies the alternative terms of GP alternative terms are positive and negative. So one is positive, next number is negative, then positive, then negative. If that's what we observe in a GP, then R, that's the constant term of the GP, it becomes negative terms. Right. Next, if we multiply the common ratio with any term of the GP, we get the next term. Or you divide any term by the common ratio, you get the previous term. Right. So that's a very well-known fact. The next one is R can be one of the following, right? You can have the R can be, I know that this is positive, or this can be negative, or this can be even imaginary. Any one of them, right? Now, we have a variety of, or the types of GP that are decided by looking at the value of R of that particular GP. For example, let us say the R is equal to 1. Okay, then the geometric progression is said to be a constant, the constant geometric progression. Obvious, because R is 1 means every term you multiply by 1, you keep on getting the same terms throughout the GP. Right. Then if the R is complex, then the GP is said to be imaginary. Imaginary GP. Right. Then we have varieties of GP which is said to be increasing or decreasing depending upon A and R values combined together. So let's try to write a very small table over here to trace out whether a GP is increasing or decreasing. Okay, so let me write A here and R here. Okay, so if A value is greater than 0 and 0 less than R, right? A is greater than 0, but R is between 0 and 1. You see that the terms are going to decrease. So this is said to be it's a decreasing GP. So this is the result of GP. Okay, and a second case is say A greater than 0 and R is also greater than 1. This means when I multiply by R to any value greater than 1 continuously, you see that the terms are going to increase. So this is said to be increasing GP. Then let us say the value of A is less than 0 and R is less than 1. So smaller value is getting multiplied by greater than term. So terms will keep on reducing. So this is said to be decreasing. Decreasing GP. And the final set is A less than 0, but you have 0 less than R less than 1, right? So A is less than 0 and I'm multiplying by a number, right, which is between this. This actually keeps on increasing, but increasing on the negative side. So, but still we call it as a increasing GP. So the types of GP can be decided based on the values of A and R, like this. So simply by remembering this table, we will be able to decide whether the given GP is increasing or decreasing depending upon the values of A and R. All right. Now, let us go for simple problems based on this concept, right? I just have to look at this table or its previous 2 points to decide whether the particular GP given is increasing or decreasing. So, okay, this is -2, -6, -18, and so on. So I am supposed to look at the A value. I can see that A is negative, that is -2, and R is equal to second term by the first term. So this is equal to 3, right? So I can see that A is less than 0 and R is actually, right, greater than 1. A less than 0, R greater than 1. I just have to go back and check this. A less than 0, R greater than 1 is this, and it is a decreasing GP. All right, then let's go to another question. Mm, This is -8, -4, -2, and so on. So I can note that the A value is -8 and R value is the second term -4 by -8, that is equal to +12. So A less than 0 and the R value in this case is between 0 and 1. So A less than 0, R is between 0 and 1 is this case. So this is said to be the increasing GP. Okay. Now, let us solve some of the problems based on checking whether the given sequence is a GP or not, right? By looking at the last term. So let's go for one case where if the Tn is equal to 2 to the power 2n minus 1 divided by, right? Find whether the given sequence whether the sequence is GP or not. So this is the question we are writing. 2 to the power 2n minus 1 divided by 3 is any nth term. So recall how we solved similar problems in AP. So Tn would have been given and our intention is to find out that if Tn of a sequence is defined by that equation, find whether that whole sequence is AP or not. So recall, right? I have to write the Tn first. So normally Tn will be given. And when the Tn is given, what we have to do? First, find the Tn minus 1 by replacing every n in the equation by n minus 1. That's the first objective. Once you do that, in AP, we used to subtract, perform Tn minus 1. When we take a difference, in the result, there should not be any term n present. If at all there is a n present in the answer, then that is not an AP, that is some other sequence. If this difference Tn minus 1 has no n, then it was called as AP. Very similar to that, now we will solve these problems to check whether the sequence is GP, but instead of finding the difference between Tn and Tn minus 1, we divide Tn by Tn minus 1 because that ratio has to be a constant. So when I divide Tn by Tn minus 1, I should get a term or the answer without n. If you get that, then the answer is yes, it is a GP. If you get the term containing n, you will say that no, the sequence is not GP. That's all. Very straightforward. Let's solve the problem. Okay, so you can see that the Tn is given like this. So if I try to find the Tn minus 1, then I am supposed to do 2 to the power. Every n has to be replaced as n minus 1 whole divided by 3. So this should be 2 to the power. There is a 2n. This is 2 into minus 1 is minus 2 minus 1 whole divided by 3. So this means the Tn minus 1 is 2 to the power 2n minus 3 divided by 3. Right. So in order to find the whether the sequence is GP or not, I should divide one by the other. So what I do, Tn divided by Tn minus 1. So Tn is 2 to the power 2n minus 1 divided by this is 2 to the power, okay, there is a by 3, so let me write that. So divided by 3 whole divided by, this is the numerator. So I have to write 2 to the power 2n minus 3 whole divided by 3. So this is equal to, normally what happens, if something is in the denominator of the denominator, that goes to the numerator. So this is 2 to the power 2n minus 1 divided by 3 multiplied by 3 divided by 2 to the power 2n minus 3. So 3 will get cancelled. Let us try to split the terms like this. That is equal to 2 to the power 2n into 2 to the power minus 1, because that is 2 to the power 2n minus 1. Similarly, I have 2 to the power 2n into 2 to the power minus 3. Okay, so now the 2 to the n cancels. 2 to the minus 1 is, it goes to denominator, like 2 to the 3 divided by 2 to the 1. So 2 to the 3 is 8, 2 to the 1 is 2, this is 4. So the answer is 4. Since this answer, after the division, we have no n present in it. So that means this particular sequence is geometric progression, right? So you can write the answer like, so given sequence is the geometric progression. Okay, so I'll give another question for you to solve now. So the Tn is equal to 2 into 3 to the power n plus 1. So Tn is given as Tn is given as 2 into 3 to the n plus 1. Right. If I want to find Tn minus 1, 2 into 3 to the power n minus 1 plus 1. Okay, so this means I can try to write this as, okay, so this is equal to 2 into 3 to the power n into 3 to the power minus 1 plus 1. So the 3 to the power minus 1 can be written in the denominator like 2 into 3 to the n into 1 by 3 plus 1. So I'm going to write this as 2 into 3 to the n, right? The divide by 3 I'll take as common. So that is 3 into 1 is 3 whole divided by 3. Okay, right? So this is the t to the n minus 1. We cannot further reduce this. Okay, so now in order to find out whether the given sequence is a GP or not, I have to divide one by the other. So therefore, take the ratio Tn divided by Tn minus 1 is nothing but Tn is 2 into 3 to the n plus 1 whole divided by, this is 2 into 3 to the n plus 3 divided by 3. So the final answer I can write, the 3 in the denominator goes to the numerator. So 3 into 2 into 3 to the n plus 1 whole divided by 2 into 3 to the n plus 3. Now if you observe, you cannot cancel any of the term, and this answer has n in that. You can see 3 to the n, 3 to the n. Right? We have n present over there. As n is present over there, this indicates that this particular sequence is not GP. So there should not be n in the ratio when we take it. So because of that, right, we can say that this is not a GP. Okay, we'll move on to the next topic, and that is the general term of AP. Right. So the first concept is the nth term from beginning. Nth term from beginning, we know that it is written as Tn is equal to A into R to the n minus 1. And since this is the last term, we can denote it as L for our reference. Okay, here all the values of n belongs to the capital N. Any n you write will belong to the capital N. So the anyway, the Tn, which is A into R to the n minus 1, becomes the last term, right? Provided we are considering the finite GP. All right, now let's move further. So in the next case, let us try to find out the nth term from last. If at all I want to calculate the nth term from last, then I am going to use this technique. So the second one is nothing but the nth term from last. Okay, now the first term from let's try to do a quick derivation of that. So if I want to find out the first term from last, this is nothing but it is denoted as, say, I'll write T1 dash. So T1 dash is nothing but L. Okay, fine. Then let me write the second term. Let's try to denote this as T2 dash. So T2 dash is, I have a term, I divide by R, I get the previous term. So this has to be L by R. Right? Similarly, if I want to write the third term from last, this is T3 dash is L by R, so L by R square. All right, in the same fashion, let's try to move on and let us try to write the last term, right? Last term from the last. Okay, so this is something like I will write nth term from last. That is denoted as Tn dash is nothing but I can see that this is L divided by, I can see third term has power 2 in the denominator. So nth term should have 1 power less than that. So this has to be, right, r to the power n minus 1. Okay, so this is the term again. In every case, all the values of n belongs to the natural numbers, that is capital N. All right. So let's try to find out what is Tn dash. Tn dash is nothing but L divided by R minus 1. But what is the L? L is the last term, right? That is considered from the beginning of it, in the sense from the left to right. So L is equal to A into R to the N minus 1 divided by R to the N minus 1. You can see this is cancelling. It is A. First term, right? You get this. Okay, now let us try to write another property that is very useful, right? We'll use this later. So if at all I try to write Tn into Tn dash, then we need the answer. Tn is equal to A into R to the N minus 1 into Tn dash. If you see from the above equation, it is L divided by R to the N minus 1. So Tn dash is equivalent to A into L. A is the first term, L is the last term. Right? So in a finite GP of n terms, the product of kth term from beginning and the kth term from the end is independent of k, and it is equal to the product of first and the last term. Right? Any Tn into Tn dash. This n can be any k. So any kth term from first and any kth term from last equal to, right? It's a first term into last term, the product. That's all, right? So we can try to remember this, and this is very useful property of the geometric progression. Okay. Let us move further. All right. This is a node for us. If let us say we know only A and L, how to find out R? If A and L of a GP. So it's with the standard notation. A stands for the first one, L stands for the last one, right? Known, then R can be calculated as, right, L divided by, this is A, whole raised to the power 1 divided by n minus 1. So the 1 by n minus 1 is actually a power. All right. Then this is another note. Right. So let us try to write if A, comma B, comma C are in GP. So let us assume that the three terms which we are considering, A, B, and C, they are in GP. Right. If that is the case, then the common ratio can be found as B by A, that is equal to C by B. This implies I can cross multiply. B square is equal to A into C. This is one condition. Okay. If that is the case, let me square the above equation, that is B square by A square is equal to C square by B square. So this implies A square comma B square comma C square also in GP, correct? Because it maintains the same ratio like the previous one. So if you have, right, if you consider the three terms that are in GP, then their squares are also in the GP unit, right? So this is what is the conclusion that we can derive from this concept. Okay, let's move further. And now we'll solve, say, some problem based on whatever we discussed so far. Okay, so if in a geometric progression, the first term is A, third term is B, and let us say the n plus 1th term is C, then find the 2n plus 1th term of that GP. So first, third and n plus 1th terms have been given over here, and we are supposed to find the 2n plus 1th term of the same GP. Okay. So first term is A, then what is the equation for third term? T3 is equal to A into R square, correct? Let R be the common ratio. A is the first term, right? So you can see A is the first term they have given. So A is the first term, R square is this, right? That is nothing but the third term. What is the third term? That is B, correct? So A into R square is equal to B is my conclusion from the given statement. So this means R square is B by A, right? I can say that R is equal to square root of B by A. I will come to know the common ratio. Right. Then let us try to write the n plus 1th term. What do you mean by n plus 1th term? So if I want to write Tn plus 1, this is A into R to the n. That is given, right? That is given as C, right? So this implies if I want to find R to the n, then I can write C by A. Okay, now let us try to write what they have asked. They have asked the T 2n plus 1, correct? So T 2n plus 1 is A into R to the power 2n, correct? So this is A into R to the power n to the power 2. So A into, what is R to the n? Just now we have written it is C by A, correct? C by A is square. So this means it is A into C square by A square. So A and one of the A cancel. So T 2n plus 1 is a C square by A is the required answer. And this is present in one of the four given answers. Okay. Then let's move further. Next question. If m plus nth term of GP is P and m minus nth term is Q, find the mth term of the same GP is a question. So m plus nth term is P, m minus nth term is Q. Find the mth term of the GP. So they have mentioned that the T m plus nth term is nothing but we can try to write it as A into r to the power m plus n minus 1, that is given as P. Right? Similarly, they have given T m minus n is equal to A r to the power m minus n minus 1 is equal to Q. Okay. Now, if at all I want to write the mth term can be obtained by multiplying them, right? So that implies if I try to multiply a into r to the power m plus n minus 1 into a into r to the power m minus n minus 1 is equal to, right side is p and q, p into q. So this is a square into r to the power m plus m is 2m, n and minus n will cancel, minus 1 is minus 2 is equal to pq. So if at all my intention is to calculate the Tm has to be a into r to the power m minus 1, right? So this implies from the above equation I have to take a root on both sides, right? So that is a square into r to the power 2m minus 2 is equal to pq. You can actually take square root on both sides. So when you take the square root, left hand side becomes a into r to the power m minus 1. That is nothing but root of pq. This itself is tm. So m, this particular sequence is nothing but root of pq.